So now we're going to go into changing the variable for a two-variable function. You've done something, you've already changed the variable in integration before. U substitution is what that would be. So, for one variable, we used to have something like some integrand from a to b. We had f of x dx. We would then use a U substitution to go from some integrand from some c to d, f of u du. That's what we did with one variable. Now we're going to do it with two variables instead. So our theorem above says let our function t of uv equal xy, and x is going to be defined as the function g of uv, and y will be h of uv. It has to be 1-to-1, and this C1, this just means continuous. Transformation with non-zero Jacobian. And so non-zero, it's going to be a positive number because we're going to take the absolute value of it anyway. So anyway, on the interior region of S in the UV plane. So it's going to map S onto R. So we've got an S and an R here for the R onto S. In the XY plane, if F is continuous in R, then we have this below. So this is our original function with a relation of X and Y with some D area. And we're going to convert that to our F there. And we're going to note that we're going to be multiplying our H function by the absolute value of the Jacobian. What's inside the absolute values is the notation for the Jacobian, which also looks like it's in absolute values when it comes up, but really it's a determinant. But anyway, and then we're going to take that with du dv. So I've got a problem down here, and we're also going to try to follow these problem-solving strategies for doing this. So number one, they want us to sketch the graph. Well, that's already done below. So our graph is down here. It goes from the x values of 0 to 2, it looks like, and y goes from 0 to 1. So our x values go from 0 to 2, and our y values go from 0 all the way up to 1. Depending upon the region of the integrand, choose a transformation for x and y. Well, those are given. So our different transformations, we're going to be using u as y minus x, and v is equal to y. So our transformation has been given. Our first step is going to be for this number 3. We need to determine the new limits of integration in the UV plane. All right, so we'll get back to what this is. We're going to do the transformation first before we actually integrate this number 390. So we're given the information. Let's figure out where we're sketching here. All right, so this line on the left, this is simply y equals x, right? Up top, well, this is just simply y equals 1. And we have the right side of our parallelogram here, we've just shifted over by 1, essentially. So this is equal to y is equal to x minus 1, shift of 1 to the right. And finally, our bound below is y equals 0. So those are going to be the 4 that we're going to use. So if we take y equals x, the first one we did, this is equivalent to saying y minus x equals 0. And now one of our transformations is the u, right? And u is y minus x, so this just simply means u equals 0. Now all right, so we did this one. We're going to do this one here. So if we take y equals x minus 1, if I rewrite that, we can get our y minus x, which we know to be our u. That's going to equal -1, which means our u equals -1, which means our u is going to be between -1 and 0. So our lower bound will be -1, our upper bound will be 0 when dealing with u. All right, so let's take a look at this one here. So if I take y equals 1, since y is equal to v, that simply means v equals 1. And our lower one, y equals 0, that simply means v equals 0. So similarly, we're going to go 0 less than or equal to v less than or equal to 1. And those are the different variables for the integrands that we're going to have there. So what that's going to give us now is our integral over the region R of, we're given y minus x, and then it's what, dA, right? So we're going to do the v in the outside and then the u. If you look above, we're going to go it as du dv, so our u will be in the middle. So our first one will be the v values. So this will go from 0 to 1, and again, this is the v. Our u goes from -1 to 0, and then we're given this y minus x, but that's simply u, right? Y minus x, this is equal to u. So that's where that comes from. And then we need the Jacobian. So, we need the well, I guess this just here, j of u comma v. Right? And then we need the du dv. This is what we have to solve for ultimately. Well, this is an easy integral, except of course we haven't done the Jacobian. We've went over how to do that in the previous video, but let's write that down. Let's pick a different color, go in blue. Remember, well, let's just do this. Jacobian of uv is the determinant, and again, this is dx du, so the partial derivative with respect to u, dx dv, excuse me. This is dy du, and then this is dx dv, and this is dy dv. This is the determinant, right? So what are our values here? Our function there, I guess we have it there. So this y minus x. So if we have y minus x, then dx du is going, let me rewrite the x. So if we take this derivative with respect to what our u is our u is equal to y minus x, and v is equal to y. So y minus x, take a derivative with respect to x. The y is a constant that's going to equal 0, so it's just going to equal -1. And the y du will equal +1. So if our v equals y, dx dv is equal to, well, 0. because there's no x in there. That's just a constant derivative of constant 0. And then dy dv is equal to 1, because derivative of y is 1. So we're going to put these in. So -1 for our first one, +1 for our second one, 0 for our third one, and 1 for our fourth one. And we take the determinant the standard way, down diagonal first, minus the up diagonal. So that's just -1. However, we need the absolute value of -1, so that's 1. So let's scroll over a little bit. I guess we can do it here. Go back to our green. That means we're going to use 0, 1, -1, 0. Our u, so it's just u. The Jacobian, or the absolute value of the Jacobian is just 1. So, well, when we integrate u, that's going to be equal to u squared over 2, which we're evaluating from -1 to 0. And let's actually bring this down. Let's start it down here. All right, so that means we go from 0 to 1, and I get a 0 minus -1 squared over 2. Well, that's just +1 and then another negative, so this is -1 half. Okay, and we then take an integrand of that, this time with respect to v, and that equals -1 half v. That's going to be evaluated at 0 to 1, and that's going to just be -1 half. That should be our final answer. It's a little involved, but that's how you do it. And